All right, welcome to Chapter 4, Section 5, Scatter Plots and Lines of Fit. This is for IM1, or Integrated Math 1. So before we get started, I'm just going to go over the screen like I normally do. So on your screen, you will see a due date before attempts. I don't get to see that on the teacher preview, but you should always see it on your screen. Number of attempts here, so I'm on number 1 of unlimited attempts. This means I can submit this assignment as many times as I would like. Doesn't matter how many times I submit, I can just keep on coming back in and trying over and over and over again. We don't limit that one. Number of questions, this just tells you how many this particular assignment has. So this one has 6 questions. It can be anywhere from 1 to 10 questions depending on the section. Grading policy is always best score, so whichever attempt is the best one is the one you get to keep. And partial credit's enabled, which means if you answer 1 of 6 questions, you get credit for the 1 question. Doesn't mean that if you answer part of a question that you get credit for that. It needs to be the entire question is answered and correct, and then you get credit for it. So once you start your homework, you must finish it before you can work on anything else. What that means is if I click start down here, then on your screen, this is the other piece that you see that I don't on my screen, but on the student screen, you will see a submit assignment button down here in the bottom right corner. We always click that button when we're leaving this screen. So even if we've only answered the first question here, we still go ahead and click on submit assignment. Number 1, it calculates in the grade book, shows your teacher what you've been working on. And number 2, it doesn't lock you out of all your other assignments, which is a big one. So the assistant will automatically assume you want to come back to this assignment if you don't submit it. And it won't let you work on anything else. So just getting a good habit of always clicking that button. It saves your progress, so you start back up where you were when you clicked submit assignment. Make sure you actually, click check on any problem you're on, because it's not going to save things that you've typed in if you haven't clicked check. You actually have to have the question correct to save your place. All right, so the 3 buttons on the side here, we have explanation, example, and message center. So explanation, it will tell you you're going to lose your question attempt on this one because it's going to show you the solution to this question. So that's definitely a very cool feature where you can get an explanation right here instead of looking at another example. But it's not going to give you the answer and then let you come type it in. You're going to have to come in on another attempt and try that one. Example will literally just give you an example, something very, very similar to what we're looking at. So it's based on type. It doesn't look like I can move that screen around, but it's the type of question that we're looking at. So it's a very specific example it gives you. And it'll walk you through exactly what it wants you to do here. So, and show you exactly how to answer the type of question too, so that you can kind of see that. And I think if we click, oh no, it's not letting me click on those, but the little cursor changed. When we do this on the other screen, these will be drop downs that we can choose from. And then we have the message center, so you can click on this, type a message to your teacher, and it will attach this question to the message. So very, very easy for us to respond and know where you need help. Okay, so let's go ahead and take a look at this question. For each situation below, identify the independent and dependent variable. So we've talked about this in other videos before. Independent variables are quite literally not dependent on the other one. They're not affected by the other variable. So that's going to be our input. That's what we put into the equation. So the independent variable is always the x value, or whatever the x-axis is. I'll say x-axis, because sometimes we don't always have x values where they give us some other variable, but it's whatever is on the x-axis, which is usually x coordinate, or the x variable, but sometimes they'll give us other things based on word problems, right? They sometimes change that up. The dependent variable is dependent. It changes based on the independent variable. So this x has an effect on it, and that's our y-axis, or our y-coordinate. So that they directly have effect on one or the other. So when we're thinking of independent and dependent, we want to take a look at, okay, these are the 2 things I'm talking about. Which one affects the other? That tells me which one is dependent and which one is independent based on there. So it should be pretty obvious usually to tell the difference. Sometimes it's not as obvious if we're not kind of separating out the 2 pieces correctly. So that sometimes makes it a little difficult. So we'll go through and we'll take a look at that. Maya makes necklaces for her job. The table below shows how the number of hours she works influences the number of necklaces she made. So if we think about this, and they already told us X and Y, and I know I already kind of gave you that idea, but if we think about the number of hours she works and the number of necklaces she made, she can go to work and sit there the whole time, right? And that's not necessarily going to change anything. Well, actually, it would change anything. If she just sat there and didn't do anything, that means no necklaces were made, right? But if she sat there and worked her butt off, now we have a whole bunch of necklaces made. So the necklaces are being directly affected by her work, how many hours she's working. We're going to assume that she's a good worker, okay? That she's sitting there working the whole time. We're going to assume that she's not just sitting there not working. But if she only makes one necklace, it's not necessarily going to affect the amount of hours she works. She should have, still gotten the same number of hours. It just might mean that she was working a little slower, something like that. So one has a direct effect on the other, and the other doesn't really change the number of hours she worked. If she only made one necklace and she was there for 8 hours, then she only made one necklace. But if she was there for 8 hours and she made 40 necklaces, cool beans, she was very productive. But the number of necklaces actually created doesn't change the number of hours she was there. As long as she's a good worker, it should be pretty consistent, but it just kind of depends on what we're going for there. So thinking of it that way, we want to go independent variable. That's going to be the number of necklaces. Sorry, the hours. I'm just being all confusing here. The number of hours she worked is independent, right, of the number of necklaces. But the number of necklaces will depend directly on how long she was there. So if she's only there a couple hours, she can't make as many as if she was there all day. So that's going to directly depend on how many hours was she there. So that's the number of necklaces. All right, let's look at this one. It says Raphael takes a certain medication. The graph below shows the amount he sleeps, shows how the amount he sleeps is affected by the amount of medication he takes. So we have amount of medication on the bottom here, and we have amount of sleep on the side here. Remember, this is our x-axis, this is our y-axis, and I know I already kind of gave you that idea here, x and y-axis for independent, and that's how it's always going to work out. So if we think of the amount of medication, that's on the x-axis, so that's going to be our independent variable. And the amount of sleep he gets is dependent upon the amount of medication he takes. So for this one, if he takes 20 milligrams, then he sleeps 7 hours. If he takes more, if he takes 50 milligrams, then he only sleeps 4 hours. So the more he takes, the less he sleeps, it looks like, is what this relationship is. But if by chance, like if we're talking about the amount of sleep affecting the medication, well, if he sleeps 8 hours, that's not going to affect how much medication he takes. Only the amount of medication will affect his sleep, it looks like. So it must have some kind of stimulant in it that keeps him awake, right? That seems like what's happening there. So independent variable, so that's going to be our medication. Because medication is independent of the amount of sleep he gets. The sleep doesn't directly affect the medication he takes. But the amount of medication he takes does affect the amount of sleep he gets. All right. So let's keep moving here. We have the table below shows the number of miles run and the number of phone calls made yesterday by each of 6 people. Create a scatter plot for the data. So we're comparing the number of miles that somebody runs to the number of phone calls they make. For whatever reason, we're comparing these two amounts. And they're already showing us that they want the number of miles on the x-axis, they want the number of phone calls on the y-axis. I don't know that there's a direct relationship between these two types of data, but we might be comparing to see if there is. So a scatter plot means that the dots are going to be kind of all over the place. They could be in a somewhat linear fashion, meaning that they're kind of grouped and it looks like a line, or they could just be scattered everywhere. So let's see what they look like when we do this. So if we go 1 mile, then we make 9, I gotta click on the thing here, then we make 9 phone calls. 3 miles, we only made 4 phone calls. 6 miles, we made 10 phone calls. 8 miles and 8 miles and 7 phone calls. And we had 9 miles and 13 phone calls. And then 10 and 2. I think this is a little bit more of a personality question on whether or not you want to be making phone calls. There doesn't really look to be any relationship between these. They're just kind of spread out all over the place. So I didn't expect there to really be a relationship between the number of miles we run and the number of phone calls we make. Unless maybe we're just running all day and we can't make phone calls because we're running. Although you can make a phone call while you're running. But this just shows, these points are not really related at all. They're all just spread out in kind of a cloud, right? There's no real function that we can see from these. They're just all over the place. So if we look at the next guy here. So this is another scatter plot, but this is, and when we're looking at scatter plots, we've been focusing really heavily on lines. So for quite a few weeks now, we've been learning how to graph lines, how to write equations of lines, the relationship between the pieces of the line, with the slope and the intercept and then points. Now we're looking at a scatter plot because information in real life doesn't happen in a linear function all the time, meaning a straight line. Sometimes it happens like this, where we have information and it's kind of all over the place. But what we can see is there's a linear pattern here. I can kind of connect these in a line. They're going down kind of together in a line. So this still has a relationship. They're just not as tight a relationship as a straight line, and they're all on the line. They're a little bit around the line. So the data points in the scatter plot below show the amount of time spent watching television and the amount of time spent doing homework last week by 24 high school students. Draw the line the best fit for these data points. It doesn't have to be exact line of best fit. Just do your best approximation. So the line of best fit, that's where we're going to kind of picture a line going through this stuff. And when you do a line of best fit, you basically want there to be somewhat the same number of points on either side of the line. So you don't want it to be, too far up or too far down. But there's more than one line of best fit. There isn't just one answer to this one. Some students may get it in one spot and some students may tweak it just a little bit. That's okay as long as it's pretty close to the middle of the data. And if we think about this type of data, we have watching television on the bottom in hours, and we have time spent doing homework on the side here. So if we go back and think about dependent and independent variables, it looks to me like the more time we watch television, the less time we do homework, which time-wise would probably make sense. If I'm spending my time watching television, I'm probably not spending my time doing homework. I have less time to do homework because I used it to watch my TV. So this negative relationship makes sense. As I do one, I have less time to do the other. As I do watch less TV, I have more time to study or do homework. So there's this very specific relationship here. And we can definitely see that idea. And the amount of time doing homework is going to be directly affected by how much TV I watch. I would also think actually the amount of time I spend doing homework could also be directly affected by how much TV I'm watching. I could kind of do dependent, independent variable either way there. Because if I'm using my time to do homework, I don't have the time to watch TV. If I'm watching TV, I don't have the time to do my homework. So they could have been flip-flopped either way here. So I'm just going to go ahead and pick a point here, kind of in between. And then I'm going to go down, and that looks like there's the same number of points about on each side. I'm just trying to get it in between here. So I'm going to go ahead and click check, and let's see. Perfect. It liked that line. So if I would have put it too high, if I would have put it above all the points, it wouldn't have liked that, or below all the points. Or even if I did it like a little diagonal here going off to the side, it also wouldn't have liked that. Make sure you're going right through the middle of the information. And we're going to use this line to make predictions. So there's actual things that happen. Those are the points. And the line is our prediction line. So this is just something that we can use. That's why we draw a line of best fit. All right, the scatter plot shows the weight of the fuel efficiency for each of 24 vehicles. The weight and the fuel efficiency. So we're comparing the weight of the vehicle to how good it is with, miles per gallon as far as, what's its fuel efficiency. Also shown is the line of best fit for the data. So they gave us a line already. And it looks a little bit skewed this way. That's because we have these outliers here. So it kind of got skewed a little bit. If I were drawing this, I'd actually probably ignore these and draw it through the center here, because that's the average data instead of looking at these outliers. But they're looking at the outliers. That's why they did it a little bit crooked there. For these 24 vehicles, as weight increases, so here we have weight along the bottom, as the weight is increasing, so we're going to the right here, fuel efficiency tends to, so if we look at the data here, it tends to drop down. As we're going up in weight, we're actually dropping down in fuel efficiency, right? We can see this negative relationship here. So it's going to decrease fuel efficiency as the weight goes up. And hopefully that makes sense. The heavier the car, the more fuel it's going to use to propel it forward. So the fuel efficiency is going to go down. For these 24 vehicles, there is blank correlation between the weight and the fuel efficiency. So this is something we need to know, the correlation. If I click this drop down, correlation means how closely are they related, number one. And number two, it also has to do with is it negative, positive, or is there no correlation at all, meaning it's just a big cloud. But if it's a positive relationship, that means that it's going to be going up. So we have to think about our slopes, right? And we've done this before in class where I have slope man like this. So he's my little upset guy. So here's a positive slope. And here's a negative slope. And it's just his little like face here, right? So he's my slope man, and he just helps me remember slopes. So here's positive. It's going up from left to right. His other eyebrow is going down from left to right, so it's negative, and that's why his eyes are plus and minus. This is undefined, and this is 0 for his nose and his mouth, but we're focusing on positive and negative right now. So with this one, I can definitely see it's going down from left to right. This is a negative correlation between the two. Using the line of best fit, we would predict that a vehicle weighing 4,000 pounds would have a fuel efficiency of approximately, so if I'm looking at the line of best fit, if I go to 4,000 pounds and I go up here, I can see that this crosses pretty much right over 25. So I'm using the line of best fit, not the points, the actual line here. So I'm going to go down here and I'm going to go, okay, 25. That seems to be the closest to me as far as where the line lands. Go and click check. So it's a prediction as far as that goes. With this one, I can see this car here was 4,000, but its fuel efficiency was much lower than 25, even though the line of best fit's up here. Although if we ignored those outliers, it'd actually be closer to where I think it should be. So it's one of those issues of depending on it if you're including or not including those pieces. All right, so the scatter plot shows the time spent texting and the time spent exercising by each of 24 students last week. So they're saying on this one, the more I text, the less I exercise. So texting apparently takes away our exercising ability. So depends, I guess, on how many texts you send out. But if you're spending, 10 hours texting, that's a lot of hours in the day to just be sitting there staring at your phone. So you don't have those hours to exercise. So that might make sense, right? We're spending time doing one as opposed to the other. So we can use this equation here. They drew the line of best fit for us, and then they created the equation. To answer the questions below, so we're going to give exact answers. We're not rounding any approximations. We're giving an exact answer, whatever is worked out here. So it says, what is the predicted time spent for a student who doesn't spend any time texting? So if they don't spend any time texting, let's go over here to our equation. Negative 0.75x plus 8.65y. Well, if they don't spend any time texting, this would be 0, right? So no time texting at all, which means that would be 0. So the time they spend exercising should be 8 hours and 8.65 hours of exercising. I'm not really sure that not texting is the only thing that will push you into exercising, but we're going to pretend like this relationship exists between these two. All right, so for an increase of 1 hour in the time spent texting, what is the predicted decrease in the time spent exercising? So let's go back to our equation here. So if we know this is kind of our starting point, if we're not doing any texting at all, we start at 8.65, and then we want to know what is the decrease for every hour of texting that we add. We're asking about the slope there. What's the change every time I add an hour? So we just go to our equation here and say, okay, well, my change every hour is going to be negative 0.75. Negative 0.75. So they've just asked me to grab pieces from the equation so far. They haven't asked me to plug anything in yet. Just, do I understand the equation at this point? So remember, we have y equals mx plus b. We practiced this for quite a few weeks. So y equals mx plus b. So b is my starting point. That's my y-intercept. So that's where I start on my graph. And then my change is the m here that's being multiplied by the x. So those are the two things we practiced a whole lot in the last couple of weeks. It's just those same two ideas. So now part C says, what is the predicted time spent exercising for a student who spends 6 hours texting? So I can look at my graph here and I could go up to 6 hours and I can see that it crosses, it's going to be a little more than 4. Don't do any guessing. Don't do any rounding or guessing or, I think this is 4.2. Okay, that's great that you think it's there. We need to actually prove it. Okay, so what we're going to do is we're going to come in here and we're going to write 6 hours. So I'm going to multiply this all out. I'm just plugging in, instead of x, I have 6. And what we're doing is the same thing we do with any other equation. If x is 6, what is y? So look at that. They gave me a calculator here too. That was very nice of them. So I have negative 0.75 times 6. So this is saying that it's going to be a decrease of 4.5 hours of exercising from texting for 6 hours. So it's not a direct, if I text for 6 hours, it takes 6 hours away. It's taking away 0.75 hours every time. So y is going to equal, we want to take this number and add 8.65. Why isn't it doing it? Plus 8.65. So we have 4.15 hours. So this is how many hours we're predicting they were exercising. And I guessed 4.2 just by looking at this. When I said this, it's like, yeah, 4.2-ish. Well, that's pretty darn close. But it wouldn't have been correct as far as guessing because it was just kind of an estimate. But I know where I should have landed about. So I'm pretty happy with that answer because it's pretty close to what I predicted. Only positives. Oh, okay. Why did it? 5. So it didn't want me to put the negative in because it's actually telling me that it's a predicted decrease. So it just wants the 0.75. That's what it was correcting me on there. Okay. So we're going to do one more of these guys. The scatter plot shows the number of years of experience X and the hourly pay rate Y. So we can see down here we have years of experience on the x-axis, pay on the y-axis. And if we look at this before they give us any information, so this is just 24 cashiers in Texas. So we know it's cashiers. It doesn't really matter who they are. But if we look at this information, as the years of experience go up, so the more years of experience I have, it looks like the pay is also going up. I can see this positive trend happening. It's going upward. The more experience I have, the more I should get paid. Hopefully that makes sense to everybody. That's definitely generally how things work when we're looking at real life situations. So we're going to write an approximate equation of the line of best fit for the data. It doesn't have to be an exact line of best fit. We're just kind of guessing. This is where I think it's an intelligent guess. We don't want to just throw a line on anywhere, but we're just kind of guessing. This is where I think it is. So the best way to do that for part A is to literally put a line on here. And let's see, I'm going to go, let's see, does that work? I'm going to step back and look at it real quick. That looks like a little bit too high, or a little bit too low, I think. Let's see if I go, oops, that's not what I meant to do. darn it. I didn't mean to put a point on there. I meant to click on the line. Let's see. Does that work out nicely? I think that might still be a little bit high, but we're going to try it out real quick just to see. So it doesn't necessarily need to be super duper exact, but it is going to expect you to be, you know, close. You want to be near a good amount of data there. So I'm going to go ahead and leave it there, and let's see how we do, because we have, you know, quite a few on this side, quite a few on that side. So I'm going to go ahead and leave it there for now. Let's see. So I started here kind of on purpose because I have my y-intercept of b. So if I'm thinking y equals mx plus b, all I need to do now, I have my b. I know that I'm starting at 8. So I went ahead and did that at $8. And then now I need another point here. Let's see. Do we cross over another point nicely? I'm actually going to rearrange my data just a little bit to make this a little easier for me. So let's see. That kind of skews it a little bit too much, I think. Most of the data on the top. I'm trying to do this nicely so that I don't have too much going on here. Let's see. It's pretty skewed off to the side. I wonder if I start, I don't think this will work. Let me start at 6. Ah, dang it. I'm playing with this just a little bit. I don't like starting at 6. I think I'm going to start at 8. Ah, dang it. I keep clicking on the wrong spots here because it's letting me click in between, so it's being very specific there. All right, let's see. That looks, actually, now that I've changed a little bit, I think that's still a little skewed, but it looks to me, I wonder if I can zoom in here at all. Can I zoom? So I want to find a nice point. So this one crosses right over a point. So this is going to be 8 and 12. So that's kind of what I wanted to see there. Why did it do that? That's weird. Okay. So I have a point of 8 and 12. So that's 8 years of experience, $12 in pay. And remember, I started with, if I had 0 years of experience, I'm going to get paid $8. So I have my 2 points, and I can calculate slope from this. So 8 minus 0 is 8. 12 minus 8 is 4. This is run. This is rise. 4 over 8. If you've never seen me do it this way, we're finding the change in y over the change in x. I just like to stack the coordinates real quick because my x's and my y's are lined up. So it's the same idea as doing the formula, just not necessarily writing it correctly. We just need to make sure we're paying attention to run and rise, so we put it in our formula nicely here. So I'm going to go with dividing by 4 to reduce these. So it's going to be 1 and 2. So this will be 1/2. So I have y equals 1/2 x plus 8. We'll see if they accept this. It's been out there. There we go. So let's see. 1/2 x. Oops, why didn't the half go there? Half. And then, does it want 0.5? Oh, okay. So it for some reason doesn't want fractions. It only wants decimals. So 1/2 is also 0.5 if I did the decimal there. X plus 8. So then we're going to predict using this equation that we just made. If we're working for 10 years, like 10 years of experience, how much are we going to get paid? So 1/2 of 10, if I'm thinking of that as 5, plus 8. So we have 8, 9, 10, 11, 12, 13. We have 13. So we're going to predict $13. So if I even go here and I go 10, and I come up here to the line of best fit, that actually looks pretty close to 13, and it should, because that's my line, right? That's the one I chose. So what I just worked out should be right on the line that I did. Doesn't necessarily mean that that's not going to work out right, because look, this person's got 10 years experience, and they're only getting a little more than $10. So let's go ahead and check that and see if it likes it. Yay, it liked it. I think the line's a little bit skewed to the top, but it still is close enough that it's okay with that line. All right, so that was section 5, and I will see you in section 6.